Good morning, everyone. Today we have the new lecture of the beam element. I think everyone hear my sound. Where's other students? Dear students, can you hear me?
والله يا دكتور تمام جبتها.
Okay.
Vale.
Okay, let's start. I will share my screen. So we have the finite element analysis of beams and frames. So here we have the direct stiffness method we learned in the chapter 1 in the first of the semester. So here we have in the chapter 3 Galerkin method and principal minimum potential energy can be applied to more complex elements. So also we will learn the energy method to build the finite element, okay? So also we will have the equilibrium if we have the potential energy is minimum. Here, potential energy, what's meaning the potential energy? It is the sum of the strain energy, which is the U, okay? So I think we have some students wants to attend. Okay, so we have the strain energy and we have the potential of applied loads, like we did in the previous lecture. So here we have the pi, which is the potential energy is equal to strain energy U plus V, which is the potential of applied loads. Now, here we have V of X, which is meaning that beam deflection is equal to the interpolation function n function. So n function we have times the q, which is the nodal degree of freedom. So here we have the review of beam theory. Now we have the Euler-Bernoulli beam theory. So what's meaning the Euler beam theory? It can carry the transverse load, okay? Slope can change along the span, which is the x-axis. Here we have x-axis, and here we have the y-axis, okay? So here, meaning we can change. This is the x-axis, this is the y-axis, and the slope change along this axis, okay? So cross-section is symmetric, okay? This meaning if we have any section, okay? So this section should be symmetric, remain symmetric before and after loading. So y-axis passes through the centroid. So here we have, this is the y, this is the x. So this meaning the y-axis should pass through the centroid. Also, we have the loads applied in xy plane. Okay, this meaning that here we have, this is the have fixed and distributed load applied in the x. This is the x and this is the y plane. This is the xy plane. Okay, so the plane of the loading. Okay, so now we have the plane section normal. to the beam, okay? So axis remain plane and normal to the axis after deformation. So this meaning that the section should not deformed before and after loading. So here we have, this is the beam, cantilever beam, and this is the magnified of this part here. So here we have the y dv over dx. This is the angle. And the rotation here, theta, which is dv over dx. And this is the distance from the centroid, okay? If we take this point, so here we have from the horizontal line to this point, it is the v of x, and this is the rotation. If we look the rotation, it is the 90 degree. And this one, it not making any deformation before and after loading. Okay. Transverse deflection curve is function of x only. This meaning that if we have any, here we have, so here we have, sorry, this one. This is the deflection curve. This is the deflection curve. This meaning that we have this is the x and this is the y, and this one is the deflection. This meaning that the deflection just only variable along the x direction. Okay, so displacement in x direction is function of x and y also. So here meaning that transverse direction, this is the transverse direction, and the displacement in x direction is function of x and y. This meaning that we have the cross section, okay? This is the x, this is the y, okay? Like this. Or this is the z, this is the x1, okay? So this meaning that the y also has a effect on the deflection. So we can making the deflection in the combination between x and y. This meaning that point here, it is different from this one. The point here, it's different from this one or this one, okay? So this is depends on the y values, also depends on the x position here, okay? So it is not just only depends on the x. Here we can find, if we making the point as the fixed, so we can making just only v of x. But if we making the point as variable, if we want the point to make here or here or here, so we will at that time we will to make the deflection in the x in this changing in this direction and in the y direction also. So that's why the y of x, u of xy, which is the displacement. Here we have the initial displacement, okay, in the direction of x minus y times dv over dx. Okay, this meaning that epsilon of xx is the del of u over del of x. And we say that in the previous lecture, what is the difference between del and d? D if we have just only one variable, while del, this meaning if we have more than one variable, okay? So here we have du naught, the derivative of this one, du naught over dx minus y d square v over dx square. Okay, so this meaning that we have taken the u derivative with respect to x to get the epsilon of x. And what's meaning dv over dx? Like, what's meaning this one? dv over dx, this one. What's meaning dv over dx? This meaning that it is the theta, okay? This is the angle of the rotation of the cross section. So now we have the epsilon of xx del u over del x, which is del u naught over del x minus y d squared v over dx squared. So we write again here. So strain along the beam axis, epsilon, this is the epsilon naught or epsilon zero, it is equal to du naught over dx. So we can denote or substitute instead of du naught over dx is equal to epsilon zero, okay, minus y d squared over dx squared. So the strain xx varies linearly with respect to y. Okay, here we have the strain of xx. It is varies linearly, we say, with respect to y, and we have the strain of yy is equal to 0. So what's meaning minus d squared v over dx squared? D squared v, if we take the another derivative, d squared v over dx squared, this is meaning the curvature, okay? This is meaning the curvature, this one. So can assume the plane stress in z direction, basically uniaxial states, okay? Just we have the in the one direction. So here we will have sigma xx is equal to what's the relation between the stress and stress? It is the modulus of elasticity. This is too important, this one. E, which is equal to sigma x over epsilon. Okay, so sigma is equal to E epsilon xx. This meaning that E times what's meaning epsilon xx, this one, which is meaning E times epsilon naught, this one, the du naught over dx, minus ey d square v over dx squared. So axial force resultant and bending moment. Now, here we have the force. How can we get the force P? It is the stress times the area. And here we should take the integration for this stress, okay, this one, E epsilon xx times the dA, and the dA, it starts from the area. So this is equal to E, so epsilon stress xx is equal to E epsilon xx. So what's meaning E epsilon xx? E times epsilon naught minus Ey d squared v over dx squared. So E epsilon naught times the integration of dA minus E times d squared v over dx squared times y dA. And here, this is too important to know this one. P here, we will have that what the integration of dA is the A. Okay, what's meaning that the integration dA for the A? It's the A, area, okay? So because we have the uniform area, we don't have the variable area. So, and what is the YDA? We don't have any variation of the YDA, okay? Y times DA. That's why it's equal to 0 YDA, integration YDA. We don't have any Y times the area. That's why it's equal to 0. This meaning that just only we have this term working, which is E epsilon naught times A, okay? This is the P. And the M, it is equal to the sigma xx times minus yda. And here it's the same procedure, minus E epsilon naught times yda, which is equal to 0. This is minus times minus will be plus, okay? This we have the minus, this one is, we have the minus, it is minus comes from the equation. So times the minus after making our, this is integration y times what's meaning sigma xx, this one, okay, this is the sigma xx, okay, which is E epsilon naught minus E y d square v over dx square. So here we will have the y times the integration, and here we have a, and also we have the dA. Okay, a dA. This is dA. So dA times this term and dA times this term. So y dA, we said, what's meaning y dA? What is meaning y dA? Integration. It's equal to 0. We don't have any change in this one. So, and we have, after making the y times y will be y square. So what's meaning integration y square dA? So what the integration of y square dA, it is moment of inertia. This is important. It is moment of inertia, okay? So, and E times this one, which is the I, this is the flexural rigidity, okay? EI, this is meaning the I, okay? This is meaning the I, which is the moment of inertia. So E times I, it's flexural rigidity, okay? So, and here we have the AE, which is meaning the axial rigidity, okay, in the force, while EI, it is the flexural rigidity. What's meaning flexural? It is bending. What's meaning axial? This is the axial rigidity, okay? So here we have the we will assume P0 in the axial, P0. What will remaining here? Just only shear and moment working, okay? We will consider non-zero P in the frame element, but here we will have, so moment curvature relation, moment is equal to EI d square V over dx square, this one, EI d square V over dx square, this one. This is 0, just only we have EI d square V over dx square. This is the moment. Is it clear, this one? Okay, this is the moment. And I think you studied this one in the strength of material also. So, moment and curvature is linearly dependent. So sign convention, here we have the P positive if we have tension, and if we have compression will be negative, okay? So here we have the positive, this is the positive moment, this is the positive moment, and here we have tension, so plus, tension plus, compression minus, and also we have the shear. Here it is the positive sign of the shear. Okay, so this is the positive direction for applied loads. Here we have, for example, reaction F3, F2, F1. Here we have the moment, okay, C1, C2, C3. Also, we have distributed load, the P, and it is the upward, this meaning that positive P, okay? So, now we have the beam equilibrium equation, summation of Fy is equal to 0. So here it is, what will we have in the governing equation? So P of X, if we take any segment of this one, so we can get the P of X, this is the P of X, and this is the distance, small prism or small segment of this beam, it is dx. Here we have shear upward, okay, this is the convention positive, and if we have Vy here we'll have Vy plus dV over dx times dx. This is important, okay? So this is Vy, this is Vy, but this is the x. But if we have dx, it will be Vy plus dV over dx times dx. This is the general convention, okay, and way to get the prism or the segment. Here we have moment, you will have moment plus dm over dx times dx, okay? So we say that the summation of Fy is equal to 0. We have P of X, which is distributed load. We should multiply dx, okay, to get the concentrated load, plus we have Vy plus dV over dx times dx. This is upward, and the downward we have the Vy is equal to 0. So Vy goes with this Vy. Okay, this is important to note this one. After opening the parenthesis, we can get this positive. This one is negative. One cancel with each other. What's will remaining? We will have Px, and dx also goes with the dx. What's the remaining? We will have P of x plus dvy over dx is equal to 0. This meaning that P of x is equal to minus dvy over dx. Is it clear, this one? Okay, this equation comes from this summation of Fy. So now we will take also moment. We have the moment. This is the moment, okay? This is the clockwise, which is the negative. And we have the other one, which is the counterclockwise, m plus dm over dx, okay? So also, we have the P times the dx times dx over 2. And if we take the moment here, for example, this is meaning that the P times dx, it will be concentrated load here. This is P dx, okay? So, and times dx over 2, okay? And what's the sign of convention? It will be clockwise, which is the negative. Okay, so and we have also the v of y times the dx to get the moment, and this one it is the counterclockwise, which is the positive, is equal to 0. Okay, now we should make the manipulation simplification. Minus m plus m goes with each other. We have dx, it's a small value, times dx over 2, it will be too small. That's why we can neglect it. This is the 0. What will remaining? What the term will be remaining? This one, it is dm over dx, and also we have the vy dy. So it will be dm over dx plus v of y dx is equal to 0. So what will we have after that? So we will have after making the divided on the dx here, so the v of y is equal to minus dm over dx, okay? And this is traditionally now this one, this meaning that the shear, it is the derivative of the moment, okay? So combining three equations together, so we have P is equal to dV over dx. We have the V also is equal to dm over dx, okay? So, and if we combine this one, this equation, and this equation, and the previous one, we can get this equation EI, it is d to the power 4v over dx 4 is equal to. So how can we get this one also? If we go back again, so we have the m is equal to EI d square v over dx square. So it comes from this one, okay? M is equal to EI d square v over dx square. So what's the V? So here we have the V, okay? So MEI, the MEI d square V over dx squared. So the V, it's the equation. We will take this one. But the P, here we have the P is equal to dV over dx, and the V also is equal to minus M over dx. This meaning the P is equal to minus second derivative of M over dx squared, okay? So second derivative, this is important to let me write this one again. So here we have P, let's say P of X is equal to minus dV of Y over dx. And we know the Vy, okay, is equal to minus this one. So this meaning that the relation between the force and this one minus minus, it will be plus. So instead of Vy, so it will be d squared M over dx squared. Okay. And also we know that the EI, okay. So in the this one, let me go this one, go this one. Here we know that EIM is equal to EI d square V, EI d square V over dx square. Let me write this one. EI, okay, EI d square V over dx square. This is equal to M. And if we substitute this M, okay, here, so we can get that P of X is equal to EI D. Here we have EI. Okay, so M is equal to D squared V over dx squared here. And also we have D squared here. Outside it will be the fourth derivative of V over dx to the power 4. Okay, so this is the relation between this force and we have the here we have the V. Okay, so now you can ask what is the V here. P of X is equal to minus dV over dx. This is the derivative of the shear. Okay, and if you go back here, what is, let me show this one. So here, what is meaning the V? Here, this V, it is the displacement, okay? This is the displacement. So we take this one, here. Okay, this one, this V, okay, this is the V of X. It is not shear, okay, it is not shear here actually, but it is the deflection, okay, it is the deflection curve is function of X only. This is the transverse deflection. It is not shear. That the V capital is shear, V small is displacement, okay? You should note this one carefully, okay? So here we have the relation. This is V shear, not displacement. Okay, this is the displacement P of X E I d to the power 4 over V over dx the power 4. So the fourth order differential equation. So now we have again we have the bending stress. Now the bending stress sigma xx, if we substitute this equation in the previous equation, sigma is equal to E epsilon xx, and what's meaning the epsilon, E epsilon, this one, which is meaning the epsilon naught minus E Y E the d square V over dx square. So we can get that here. So here minus E Y d square V over dx square y minus this one minus y E y d square V over dx square y, because the epsilon naught here we don't have, it's equal to 0. Okay, so we don't have any axial force here. Okay, that's why it is the we can get the 0. Also, the moment is equal to EI d squared V over dx squared. This is the displacement. This is the displacement, not shear, please. So sigma xx now, if we have the x, which is the longitudinal axis, and y, which is the vertical, is equal to minus mxy over I. After making the d squared v over dx squared is equal to m over ei, and substitute this one here, so we will don't have any e. Okay, I'm sorry, this is the call. Let me answer this call, and also we will come back again after 10 minutes if the Zoom is finishing. Okay, I'm sorry for this interruption. So here, I think you see the sharing window. Okay, so here we have sigma xx is equal to minus ey d square v over dx squared. After substituting d square v over dx squared is equal to moment over ei. So e goes with the e, and what's the remaining? Let's see this one. Okay, so here sigma x, so let's is equal to minus ey. So what's meaning d squared v over dx squared? It's m over ei. So m over ei, okay, m of x. So this is e goes with this e. What's the remaining? Minus m of y over I minus m, this m, y over I. Okay, this is the sigma of xx, the variable with x and y. This is the bending stress. This is only non-zero stress compound for Euler-Bernoulli beam. Okay, so transverse shear strength. So the gamma of xy is equal to the del of u over del of y plus del of v over del of x. This is equal to minus del v over del x plus del v over del x. Okay, this is the equation and is equal to 0. We don't have the transverse shear strength. So, and the u of x and the u of x is equal to, we say that the u of naught minus y dv over dx. So, and Euler beam predicts 0 shear strength. So we don't have any shear strength approximation. Traditional beam theory says that transverse shear stress is tau of xy is equal to vq over id to get the stress within the section. However, so the shear stress is in general small compared with the bending stress. So potential energy is, this is the pi, potential energy is equal to u plus the v, okay? Total energy minus, plus the applied load. So strain energy, this is, we have the strain energy, the first one, strain energy density, which is the U, is equal to half sigma xx epsilon. Xx is equal to half E, so this is the substituting. E, what's meaning sigma? It's E epsilon. So it will be E epsilon square. Okay, so it's half E. So what's the epsilon? It is minus y d squared v over dx squared all squared. So this is equal to half E after opening. So minus squared plus y squared d squared v over dx squared all squared. So strain energy per unit length is equal to the integration of u naught of x y z dA. So it is equal to half E y squared d squared v over dx squared. So this is the u naught times the dA. And what's the integration of y squared dA? It is the moment of inertia I. So this is u of L half E I d squared v over dx squared all squared.